Hi, I'm Sala, and in this video we are going to analyze the full response of a spring mass system with some damping, this one in the picture, using the symbolic toolbox command dsolve. We are not going to delve into why and how this command actually solves the differential equations. There are many methods, and they are the center of usual differential equation courses. In here we just wish to get a glimpse on how that response is and understand its physical meaning. So if we review the modeling, we have this differential equation, Newton's law, mass times acceleration equal to some force balance, in which I have the spring term ky, the damping term b times the speed, and the forcing term F, positive in the rightwise direction. So if F is 0, then we have free response, and if F is non-zero, then we have forced response. The mechanical system and the reference frame has been located so that the equilibrium position is 0, the vertical pink line. Good. So with this code, I create symbolic functions of time y and f. I create real constant parameters. I use velocity as a shorthand for the first derivative of y. I use xl, a shorthand for the second derivative of y, and then this is how I input the ordinary differential equation into the symbolic toolbox of Matlab. In order to have an actual solution, I will need to replace the constant parameters by actual numerical values and the force input by a given function of time, which will be the excitation that makes this thing move. So let's do it. I will substitute in this ODE the symbolic letters M, K, B by the numerical values M num, K num, B num. So this is the ordinary differential equation to solve, but okay, we still need some issues with initial conditions and force input, because otherwise, with no further substitutions, if I tell the dsolve command to solve this differential equation, the result is sort of a horrible monster with convolution integrals, constants of integration, whatever, that no one understands. Okay, I mean, if you have done a course in ODEs, maybe you do. But anyway, we wish, to simulate spring moving and not dealing with abstract expressions and manipulating integrals. In engineering, we want to understand this in common sense language. So let's forget about this general solution and let us fix particular initial position and speed of the spring and a particular function of time. We will substitute it. So if this force is 0, as it is now, we will have the free response, and that free response is this kind of exponential times trigonometric in this case. This 1/5 is the decay rate, and this 3 square root of 11/5 is the oscillation frequency, the proper oscillation frequency. So if we plot this, we get an oscillation that goes to 0, and we discussed animation code in another video, so that we see this displacement going to equilibrium. So good. We will now inspect the result with a constant force. So if I execute again, we get this expression. It's important to realize a couple of things. First, that the exponentials that appear are the same as in free response, as well as the trigonometrical terms. So decay rate and oscillation frequency is the same. So we have a term kind of like the free response plus some other constant. Indeed, we can understand this as, if I push in the negative direction, so leftwise, if I push this to the left, then the equilibrium will displace to the left under the new force, but otherwise the dynamics keeps unchanged. So this is the physical interpretation of this constant plus something very similar to the free response. Indeed, here we see how the new position just settles at the new equilibrium position. Which one? Well, as spring constant is 2, when I move 1.25 meters, then the spring makes 2.5 newtons, so it cancels out the increment of force. So the equilibrium position moves 1.25 units to the left. So the animation of this force response is basically similar to the previous one, but moving to a different equilibrium. So this kind of response is not too different to the free response, just going to a new equilibrium. Of course, if the initial position and speed were exactly 0, then this expression, this particular thing, is called step response. So this is the textbook plot of the step response from initial equilibrium until it stops in here, and the physical interpretation, the animation, is this one. Good. Let us now try a sinusoidal input like this one. So this is not here, I multiply by 0, and this simulation is of paramount importance in, say, vibrations. Then what can we see? Well, we see a few interesting things. First, we have this term and this term that are some constants multiplying the same exponentials and sinusoidals, sinus and cosinus, that appeared in the free response. So it seems that these free response related terms appear in all simulations. That's basically true in common sense engineering, unless you prepare the initial conditions and the input in particular ways. In most of the cases, you can put here whatever function of time you wish and whatever initial conditions you wish, and in most of the cases, you will see expressions in this form with the decay and omega in the free response. Of course, why and how this occurs can be theoretically proved, but this is not a video in theory. The next important thing that we see are these terms. These are some trigonometric terms like this with no exponentials, important, oscillating at the same frequency as the forcing input. These are so-called forced vibrations that do not decay. They will be there forever. And when a lot of time has passed and this exponential is small, then this will not be present, and we will have only this sustained vibration at the same frequency as the input, and that blue thing is called steady state sinusoidal regime. So if we see the plot, we do have a transient phase in which we see some ups and downs and things from that exponentials and oscillations at different frequency. And in here we have a pure sinusoidal that would last forever with the same frequency as the input. That would be, the steady vibration of my spring. So this will be the animation. we first see kind of strange oscillations, but now we have reached the sinusoidal steady state, stationary state, and this vibration would keep forever as long as the forcing input is acting. So this is the so-called frequency response sinusoidal regime of importance in engineering in vibrations and alternating current, for instance. We can now add both components, the constant and the external vibration, and in this case we have what is called superposition, in the sense that we get the new constant equilibrium we saw before, the steady state stationary sinusoidal response, not damped, with this 4 radians second of angular frequency, and we get the decaying exponentials from the initial free response. So we have kind of free response terms in all simulations, and some terms similar to the input, in the sense that this constant appears as a constant in the output, and this sinusoidal appears as an oscillation of the same frequency in the output. This is the simulation, and in fact, we can even add initial conditions, so we get sort of the same shape but different transient amplitudes. This and this keep unchanged, but changing the initial position, it's these coefficients that change with respect to the case in which we have here 0. This is the position as a function of time, in which we have a transient regime here, and the steady state sinusoidal plus constant center at the new equilibrium regime, when all the initial exponential terms, depending on initial conditions, vanish. And of course, if we see the animation, we have here the initial transient, kind of erratic behavior, but at the end, now we are already in the steady state, sustained vibration around the new 1.25 equilibrium point, and that would keep forever, but I stop. Of course, if I change the excitation frequency, then the frequency of the stationary sinusoidal output does change, of course. For instance, in here, the amplitude is kind of larger, so we may be closer to what's called a resonance. Anyway, we'll finish here. In this video, we have shown how dsolve can solve with whatever algorithm it wishes the differential equations given force and initial conditions. We have shown that there are terms similar to the input, constants, sinusoidals, etc., and other terms similar to the free response, and the superposition of all those, it's what constitutes the force time response, and we have shown how to plot and how to animate it in order to better interpret those results. So this is it. Thanks for watching.